Cool, well welcome along guys. Welcome along to the last session of TechEd. Woohoo! I'm going to enjoy a drink later on, and I hope some of you will as well. You guys been enjoying it? It's been good? Go on, let's hear it. It's been good? Okay, excellent. Today I want to share a little bit about my love of the magic of async. My name's Mark Young. I work at Datacom here in Auckland. And I've been working with asynchronous programming and the async await framework in C# for a couple of years, since the first betas came out, with teams of all sorts of different sizes and different ability. And it's something that almost from the very beginning clicked with me. And I guess I've had a bit of a love affair with it. Anyone who's worked in my teams can tell you that. I entitled my talk, The Conjurer's Masterpiece, because for many people, async await inside C# is magic. In fact, who was it? Arthur Clarke said, any sufficiently advanced technology is indistinguishable from magic. Now that's all cool, but personally, I like the John Skeet view of magic. I love magic as long as I understand how it works. And so what I'm going to try to do today, in this last hour, is to try to show some of you guys how the magician pulls the handkerchief out from his pocket, where the last ace of hearts is kept up the sleeve, and so how the guys behind async were able to build this framework, and build a framework that's simple, easy to use, and hides the complexity, but at the same stage still gives you power, and allows you to access everything you need to do. So this is definitely going to be a coding session. I'm hoping Ivan's got tomatoes in the front to throw at me, or anything like that. Hopefully it'll be a bit of fun. I want it to be pretty relaxed. It's the end of TechEd. So I want to cover today, here's what I want to look at. I want to give you an introduction to asynchronous programming. I'm going to cover why we need it and what it is, just to make sure we're all on the same page. I'm going to then show how it works inside C#. But I want to spend the bulk of my time building it. So it's going to be me behind the keyboard, coding away. We're going to see how it goes. This could go spectacularly wrong. I've never tried a demo quite this intense before. Hopefully you've still got some brain cells left after Ivan. I'll try to tax the last few of them. And then I'm going to finish off with some practical async. I've got tips that I think you should know, but I'm very open for this being question-driven. So for those of you who don't understand things or have questions, feel free to chuck them at me, and because I think that'll be quite fun at the end. So just to get an idea of who's out here, how many of you guys are developers? Excellent. Okay, that's a good start. Cool. How many of you guys develop in C# most of the time? Yep, sweet. Okay. How many of you do UI programming? This is probably a bit less. Oh, no, okay, most of you out there. Okay, we're on the right foot. So hopefully I'm not going to lose you guys so much with the background. How many of you have used async await inside C#? How many of you understand how it works? How many think you understand how it works? Okay. How many knows what the compiler's doing? Ivan, excellent. I've only got one person to call my bluff. Feel free to call it. Okay, so let's kick into it. What is asynchrony? And why do we need it? Apart from another big word starting with A. Well, I'm not going to describe that to begin with. The earliest computer programs I remember look something like this. I know I'm younger than many of you. Back in the mid-80s, these are what I remember seeing. And from a UI point of view, they're really simplistic. We've got a limited number of responses that the user can give us at a limited number of times. And this allows us to program in a really linear manner. We can just do our straight up and down, in a line, how we think. It's much, much easier to code. But then along came these fancy pants with these things called GUIs. And yes, I did have a copy of Windows 1 and Windows 2 on my machine. And suddenly the users could interact with our system in all sorts of different ways. It was unpredictable. They could move this mouse and click on a whole myriad of options. And there were multiple of these going on at the same time. So our applications suddenly had to change to, instead of dealing with only specific input at specific points of time, into events that could happen almost any time. And into having to keep the state of these multiple windows all going. And so we launched things like Visual Basic, event-driven programming, which was a completely different model to what we had done as console. But realistically, most of the back-end stuff stayed the same. Everything below those UI and that event-driven layer up there stayed linear. We would get in a method in response to a button click. We'd go off and call a database, bring something back, maybe call a service, ship it back up to the client, and we hope we were fast enough to be able to display things in a way that the users didn't mind. My premise, though, is that over the last 5 years or so, modern development's been changing, especially with the world of web and mashups and everything else. We're now retrieving data from a whole range of sources, most of which we don't have any control over. We might be retrieving multiple feeds of data all at the same time. Again, and we need to show this responsively to the user. So modern development requires multiple processes to be happening simultaneously. But we don't always like the code that results. Sometimes it looks a little bit like this octopus. There's tentacles everywhere. So our coding hasn't necessarily kept up with the style of development that we now need to do. Now, I still haven't defined asynchronous programming. So I'd like to walk you through a couple of scenarios and analogies, still without defining it, and hoping that you pick it up. Now, there's lots of different analogies that people have used, and I'm aware that the light bulb only goes off for some people with some of them. So hopefully I can make the light bulb go off for those of you who hasn't gone off for before. If not, go see a different talk or look something else up on the internet. I'm sorry, I've failed, but it's okay. So I'd like to imagine a guy called Joe. And Joe's here, and he's got a pizza shop. Now, he's got some cooks who work for him. He's got a whole bunch of them, and he might even have some customers. Now, the thing with Joe is he's a bit of a simple bloke, and he's not really very good at multitasking, like most of us males. So what happens normally in his shop is a customer comes in and orders. They then move and wait for the order. Meanwhile, Joe takes the order to the chefs and sits around waiting while the chefs are cooking. Once the pizza's ready, Joe's able to go get it, give it to the customer can move on, and he serves the next customer, and so on and so forth. Just let those chefs keep going. Yes, I've probably got the best animations that have been done for this talk. So that there is a blocking algorithm. That's what we would normally do in our standard linear programming. It's a simple programming model. Joe takes an order, takes it to the chefs, waits for them to cook it, gives it to the customer, goes back to the beginning. But it's pretty inefficient, because Joe's sitting around all that time not doing anything. But he's not actually having to do any work. He's just standing there waiting. So in an asynchronous world, what might happen might be something like this. The customer comes and orders from Joe. Joe takes the order to the chef, but he's now free to go back to the counter and take the next order. Once again, he takes that to the chef, gives it to them, goes back, takes the next order from the customer, and now he's free to be able to serve our resulting customers. 3, 2, 1. And if you're watching the timer, you'd see that that finished a lot earlier than the first one. So the piece behind asynchronous code is not necessarily multi-threading. Multi-threading would be referring to there being multiple people behind the counter. There's only one. Asynchronous coding is all about the coordination of multiple concurrent processes. Now that's the most number of big words I've ever put on a slide. But hey, we'll get there. So this is the real big piece you've got to get in your head. Asynchronous programming is not about necessarily doing two things at exactly the same time. It's about coordinating two linear processes at the same time. And this has come from a school of algebra called CSP, if you want to look it up later, communicating sequential processes. But it really is that. So it's all about a single process. Joe takes the order, takes it to the customer, takes it to the cooks, waits for it, gives it to the customer, and goes away. How can we maximize the use of his time because there's only one of him? Does that make sense? We're all on the same page? We can all understand a pizza shop? Okay. So what might this look like in code? I don't have too many of these slides before we get into it. Well, here's a pretty simple piece of code that represents that video that you saw before. Joe's having to serve a customer. He takes the order, he goes and gets someone to make the pizza, and he waits around. He gives it to the customer. In this case, he waits for the customer to finish eating, and then he cleans up the rubbish. Bang, 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 bang. But while we're waiting for someone to make the pizza, Joe's not able to do anything. So our thread is locked and our thread is busy. So why can this be dangerous? When are the scenarios where we need async? Because async is not required everywhere. Well, the first time is when we've got scarce resources. In a UI application, there's only one Joe. We've only got a single UI thread. It's a scarce resource, so we want to make the best use of that possible. JavaScript and the web is another example. And this programming paradigm is all coming to the web as the web starts mimicking thick clients that we've had on Windows before. Or maybe resources are too expensive. Maybe we can create another Joe, but it's going to take us 30 years. So, hey, we can't wait around for that. That resource is expensive. And in .NET, thread pool threads are actually jolly expensive. Or threads in the system. We can create 1,000 threads, maybe, but if they're using a meg each, that's going to start to cost us. And maybe the thread pool only adds them slowly, 1 a second, 2 a second. That's not going to keep up with demand for many of our applications. Or maybe we've got too many connections to handle. So if you think about something like SignalR now, back in the old days, the web would be request response. You take in a request, as soon as you're finished, you finish. If you've got a long-running duplex connection, you need a thread per customer, per user. If I've got 10,000 people trying to connect to my chat client, that's 10,000 threads. That's 10,000 meg just holding that beginning of the thread memory before you put anything else in there. We can't keep doing that many. It's too expensive. So we've got to find some way of sharing the work and reallocating work amongst these threads. Everyone with me so far? Yell out at any time if you're not. So what approaches have we seen? Well, here's about the first simple one. We've got callbacks. So we create a cook. And a cook doesn't do work on our thread. A cook goes off and does something else. Think about this like a web request. We make a web request, but the work isn't happening by us. The work is happening by a remote party. And so we set up a callback to say, once you're finished, come back to me, and then I'll do some more work. So that's really simple. The problem with the callbacks, with our code, is that I've just put here what I'm going to do next, first. It's really confusing to read through some of the stuff. And so we'd end up with code that's got methods absolutely everywhere, and trying to follow through things is just really hard. Or we might have promises. This type of syntax is coming. It's available with the TPL in C# or in JavaScript. There's lots of libraries that do it. And here at least we've got the order in the right order. I give the pizza to the customer, and then I clean up afterwards. But what happens if I'm trying to coordinate exceptions here? I've got to somehow try catch inside each of these blocks or wrap exceptions and do funny things. And there's just too much ceremony. The ceremony's got in the way of what I'm trying to do. And I've lost that linear, easy process from other pieces. So C#'s great, async await. And this is not just limited to C#, this is coming in other languages as well. And Ivan will tell you that F# did it much, much better. But at least for me, in simple programming, this does it for me. It's great. So this looks almost exactly the same as our blocking method, just with a couple of extra keywords inside it. My logic looks the same. I'm able to write this, I'm able to read this, but I still get the benefits of freeing up my main thread and not blocking. And here's another example, just showing that now I can actually use try-catch and other things around that as well. So if I'm needing to do exception logic, I can do that. It looks just like a standard synchronous method. We all on the same page? Anything yell out? Okay. So now what I want to do is I want to show you a little bit of how that magic happens. So I want to go through, I'm going to sit behind the compiler and see if we can build that. So starting from scratch. Let's see how we can go. So I'm going to go back here to my desktop. And I've got code here that represents that scenario. Now if you don't believe me, hit F5. We've got our same picture up, and I'm going to click play. This is our blocking scenario at the moment. So this is our code for our blocking piece. Joe's sitting there and waiting. I've sped that up so you're actually able to see what's going on. We're going to see this animation a lot today. You're probably going to be completely sick of it by the end. But hopefully it'll allow me to code and you to see what's going on really easily. That's my hope. If it doesn't work, yeah, go have a drink. It'll be fine. So the first thing I want to do is I've got this method called getCooks to make the order. And I want to make this method so it doesn't block while it's happening. So if we go into that and just take a look at it, I've got a little bit of animation code here. This is my logic for my method. But this method here is a blocking method. It waits for 5 seconds. So what techniques have we got to be able to offload that? Well, the easiest one that we've got is the thread pool. So if I remember how to even use a thread pool, What am I doing? I'm missing an R. Thank you very much. Crowdsource code for the win. Okay. So let's just queue a user work item. And I'm going to wrap that onto a background thread. Okay, that takes in, I believe, a state or something first. Okay, so now I've put this pizza into an anonymous method that's going to run on a background thread. I can't return here because I don't have the pizza, so I'm just going to return null. Okay, to see what happens. So if I hit F5 on that, what should happen when I click play now is that Joe takes the order, gives it to the cooks, and then, the pizza wasn't ready. He tried to give the pizza to the customer. So he returned back straight away, but yes, he wasn't being blocked. Okay, so that's been happening on another thread. Someone else is doing it. So what we need is an object that represents this future work. And this in C# is called a task. So the task represents the work that hasn't finished. But I'm not going to use any objects that are actually built into C#. So I'm going to create my own one. Now, Nigel Sampson completely laughed at me when I said I was going to code this stuff up from scratch. But let's see. Now, I've cheated, so I'm actually going to create one that I've pre-done. Okay, let's do it from scratch then, if you're going to laugh like that. Task. Okay, let's see what I can make. So what we need is a Boolean or something representing whether it's finished. And I'm going to turn that into a property with a backing field. And you'll see why later, but I'm going to make a set completed on there, which is going to set is completed equals true. And I'm going to remove the setter because I don't want anyone to be able to set it back to false. So there's a class that represents something, whether it's completed or not. And we're going to see why in a second, but I'm just going to create a task with a result because we want to be able to return back our pizza object. So there's my task. And this guy here is going to have... Okay, we're done. Inconsistent accessibility, I'll make that public, and we're good to go. So there's our task. Just so my demo works, I'm actually going to copy and paste that back in. But it looks exactly the same. So that's what a task is. A task is an object that's got a single Boolean saying, have I finished yet? And the easiest way for us to use this would be, okay, well, let's create the task. So task of pizza here. I'm going to create a new one. When the pizza's finished, I'm going to say that here's my new pizza. I don't know if I could spell. And then at the end of the method, instead of returning null, I'm going to return my task. And we'll just change that signature to a task of pizza. So now I've got this object that's got a property called a result that I'm going to return back. And so down here, let's make that our task of pizza. And I'm going to call that pizza task. That comes down here. Well, the simplest thing we can do is just go while not pizza task. Thank you, resharper. Dot is completed. Thread.sleep. Okay, that's our simplest. So we've got a task coming back. Okay, and I need to go pizza task.result. 35. So this here should now look like our blocking scenario again. Okay, he's going to wait around because I've got my thread.sleep going. Well, that's no good. We're close here. We've now got this object that represents a continuation. But ideally, I want to be able to queue this next lot of work on a background thread so I can return back straight away. And I'm just going to look at my cheat notes again because that's okay. We're allowed to do this. I've got an extra piece here. And I'm just going to change my definition of the task because otherwise we won't get through this. But I'll show you what I'm doing. Oh, that was in there. That didn't work. Let's code this up from scratch. What I'm going to do is I'm going to add a continuation here. So I want to make a method that takes in some action to run when the task is completed. And this is going to be really simple. So if, when this method gets called, it's already completed, I'm going to run an action. Otherwise, I'm going to add it to a list. Let me do continuations.add the action Let's create that as a list of action, and I'm going to initialize it. So I've got a list here of actions that will happen when this task gets completed. Inside my onCompleted, for each inside our continuations, run it. So what I'm doing here is I'm registering on my object to say, if you've already finished down here, here's the code to run straight away. If you haven't finished, keep this code for later, and when you finish, run it. This here's the basis of any promises library like in JavaScript. Does this make sense? We can all see where we're going here? So if we go back to our original Joe guy, instead of waiting here, I can now go pizza task dot onCompleted, and I'm going to give it an action. And this action is going to look like that. So now I'm saying, if you've already completed when I call you, run this, give it to the customer. If you haven't completed, wait around, and when your cooking task is finished, then you can give it to the customer. Let's just run it and see what this does. I'm going to hit play. And that's async. That's the simplest way of being able to offload something onto another thread. But that's our nasty looking logic. So that's our continuation that I mentioned before, like our callback style. And we don't really want to do that. So what I'm going to do is I'm just going to change another method so you can see this. I've got my, not my give order to customer, my take order from customer. I'm going to make this a little bit bigger. I've done exactly the same thing here. I've moved this into a task property using my own custom task. And this is just taking the order from the user. So down here, what I'm going to do is take a task order. I'm going to do exactly the same thing. Order task equals take the order from the customer, order task.onCompleted, run the rest. And here's the beginning of this thing called a Christmas tree. onCompleted dot result. But can you see how we've built that? Are we all following along so far? Feel free to stop. I can go back at any time. So now what we've got is the first one when it's completed. Now we're going to run the second task. And that one might take an indeterminate amount of time and complete too. Remember, because this serve customer, this goes through and all it's doing is registering callbacks. It's finished as soon as we're at the end. Joe's free to keep doing his work and to keep running on queues. But that's starting to get a bit nasty looking. So here's where I want to take the really big jump. Here's how async has done things, and I might need to use some other slides just to really explain it. As we go through this, you can think about this almost as a list of tasks. We've got a task, we're waiting to see if it's completed, run a next action. If that's completed, run the next action. If that completes, run the next action. Wouldn't it be nice if we could just express this as a list and make something else do the coordination for us? So we can do that, and I'm just going to copy this down and make another one, IEnumerable, of our task. So we've got a task. I'm going to call this serve customer tasks. And at this point, I'm going to use one of my favorite words, yield. And I'm going to jump in and show you this. Yield, return our order task. Come back. Same thing on pizza. Yield, return pizza task. Delete. Finish. Now we've got something that looks a lot more like async. Now who here understands yield return? Who knows what that's about? Okay, let me switch back to my slides because I just want to show you an example of this to make sure we're on the same page. So here's what yield is. Yield was introduced in .NET 3.5, and basically you can create a method that returns a list, in this case down the bottom a list of numbers, but the loop inside it, or the next yield, is only run as we iterate through that method. So think something like link to SQL, where we're used to methods here that don't initially run as soon as we call them. So this yield of getNumbers is returning number 1 and number 2. But number 2 is not going to be returned in that line of code that's above 2. So the method is going to break as soon as it calls yield return 1 until the next one iterates over it. So we can see on that right-hand side, my output, I'm interleaving between these two. Internally, it's basically generating a switch statement with a state. So if I'm in state 1, okay, carry on. If I'm in state 2, here's my bit of method. I'm in state 3. We're going to leave that up for a second. Any questions about yield? Because if we don't get this, you might not get the next step. Cool. Okay, let's go back to the slide. So we've got this yield piece. So yield in this case means that we're going to go down here, run our take order from customer, and then the method's going to break return out. It's only going to return this next line when we next iterate over the method, when we next call get me my next iterator. And then it's going to return the next line, and then down here. So what I can do, actually if I just change, I'm just going to change this. So var tasks equals serve my customer tasks based on a customer. And then, actually I'll show you it just like this. If I call it like this, nothing should happen. Or only the very first thing will happen. Okay, the very first thing's happened, nothing else, because I haven't iterated over my method. So it's only run up to the very first yield. It's only run the first part. However, if I iterate over it, even if I do nothing, this will then try to run everything. Oh, pizza wasn't ready. So we've got this case here where we tried to do something and the method wasn't ready for us. Let's ignore my threading issues, even though this is a threading talk. That's okay. So what we need to do is do something with these tasks. Well, we've seen what we need to do. We need to wait for each one. So what we can do is I'm going to create up a class that's able to do this for me. Where was I? Okay. So var an async method builder equals a new async method builder. I'm going to pass in my tasks, and I'm going to get this guy here to run. So I want something that's going to be able to run and iterate over that class. So async method builder, let's create one of these guys, and I'm going to copy in this code. It's not very big, but it might take me too long to explain. So I've got this run method. Inside my run method, I'm going to pull out the enumerator. And then down here, this code looks familiar. I'm iterating through this method. If the task is completed, run the next method. Otherwise, wait for it to be completed and then run the next method. Okay, which is just iterating through that list. So I've now got this iterator that's going through my list of tasks, which remember are breaking out after every yield and not doing anything more until I call the next one, waiting for that to finish, and then continuing on with my method. By blowing any brains, we're still with me? So let's go back. Async method builder. This is the method here that's still getting called. I'm going to hit F5 on that. And now it's waiting for each one. We've got our fully async method. And this is all async is. We've got this magic of async. This is all async is at its heart. We've got continuations that we're listening on. We've got a method that's yielding out these continuations. And then we've got a method builder that's iterating over those, waiting for each one, and continuing on the next one. Now, there was a little bit more complexity behind the scenes. So just to prove this is what async is, if you think about the compiler, when you see the async word is generating this first method. If you look at the compiler, what it does is it generates a method that creates a method builder and calls run. Splits it out into these two methods. That's really what's happening. And down here, this yield return, this is the await keyword. So what I can do is I can actually, let me just ignore that. I'm going to change this yield return to the word await. And this one here to the word await. And up here I'm going to remove this guy and put the word async there. Now await isn't compiling, so we can do a tiny little bit of compiler magic and create this thing called a task awaiter. And this just wraps our own task, because remember we've used our own task and not something that's in the operating system. We can actually use any class here and await on it. And our task awaiter just has two methods, our isCompleted, which I'm calling through to my task, and a getResult. And so this looks exactly the same as our task class. So I'm calling through to it. If you look at that, this now compiles. I can hit F5. run it, and now we're back to async await. My code was completely equivalent. And that's it. Done. Can I get a round of applause for that? Yeah. So all async is this method builder, iterating over tasks, and awaiting on these results. How we use it's a bit different. Now, any questions on that code? Absolutely anything. Why did I use the result one? Okay, let me flick back to my code and let's show you that. Now the reason is that I wanted to be able to wait on a list of things that I didn't care about the type of. Okay? But why I've used the type one, I could make that an object. So I could have a task class that's got an object for a result because I need to be able to pass my result back from the method I've called. Okay, so if the result waits on, so let me just make sure I've got this question right. If the next step in the piece, so after this await here, depends on the result of the one before, depends on the kind. So here I've got an order task.result. Why have I used a typed one rather than using just a standard task for everything? A single task? Is that what you're asking?
Yeah, what I'm asking here is that there is an assumption there that every task performed results in only one flag.
Yes.
Which is not always the case. You can have different variations of results. Depending on which you will have different action to take next. This is what the unknown that could run.
Okay. So just to make sure this time I've got this right, we call a task, depending on the result of that, we might actually do different things.
Yes.
Okay. So easy. Task, a bool comes back, wait for that, if order task.result, do one thing, otherwise do something else. So that logic comes into us. We've got a type there, which is the type that the method is returning back, and we can do absolutely anything inside our callback. But there's no actual switching inside this because the async framework is really around that continuation and the resuming. Like, when should I resume the method? When shouldn't I? Does that answer your question at all?
Yes.
Okay. Excellent. Anything else? So that demo went really, really, really fast, which cool means that I've got lots of time to talk about tips and tricks and lots of time to answer questions around async. Let me just put that back to a method that's compiling, and then we're cool. So here's some of the pieces we saw in the puzzle. We had our tasks. And tasks in .NET, which are a built-in part, not my type, this is a built-in part of .NET 4, represent the results or promise from our method. So we saw that. So this is the type, this is the object that's coming back. It's either finished already, or it's not finished, or it's got an exception inside it. Okay, so the task holds all of those pieces. Our awaiter is our adapter. Now in the real .NET, that piece of code that we saw, and I'm going to show you a threading in the middle, I put the on continue onto the task because it was simpler. In real .NET, the on continue goes into the awaiter, which is the adapter in the middle. But that's really just a semantic piece. A method builder. So that's the coordination of the method. How does it iterate over our tasks? And these are all subtly different depending on whether our signature is an async void, or an async result, or an async task. Continuations are the pieces of what do we do next. So you saw that, that's just the rest of the method. And schedulers are something we'll touch on in a bit, of how do I run the continuation. So I've got this little bit of code that I need to run next. Is there anything special I have to do when I'm running it? And this is where threading and fun comes in. So I want to look at some practical async. And these are some of my tips and tricks of things that we should know. Hopefully we can get through this, and then I've got time to answer some of your other questions as well. So the first one is that task is actually really, really versatile. We tend to use task, at least naively, for all the operating system pieces in the framework that return back a task. But we can create our own tasks around anything. So we've got a framework method that doesn't return a task. We can either use task.run to run it on a background thread and wrap it up inside a task, or we can create one of these task completion sources. So what this does is creates an object that returns back a task and allows us to set it to true. It's really the same thing as that task that I showed you. But if you're going to try to create that yourself, you need to use one of these task completion sources. And so using that, you can wrap any process. In fact, you can wrap all your business processes. You can have a task completion source that, say, in a UI world, represents clicking on a button. So I can create a form, create a task that is when the user clicks on a button. And in my procedural code, I can go new form, await user click on button 2, then do the next piece of code. And the async framework deals with that. Because remember, it's about coordination of processes. Those processes don't just have to be back-end, they can be front-end as well. Does that make sense? So here's a scenario I think I used where I was trying to talk about TechEd. Waiting for all my TechEd talks to be accepted. Waiting to prepare the talks. Now, I didn't actually do this in the right order because I delivered some of my talks before I prepared them, but that's okay. We got there. We're going to wrap up business processes and tasks. Here's how we start to get fun. Make sure all tasks are observed. If you have a method that returns a task, and I'll show you why, you have to make sure that you listen to it. Well, this is not a golden rule, but this is a mark rule. If I find any code in any of my systems that doesn't do this, I'll shoot it. The basic reason around this is around exception handling. And I'm going to code, actually we've got time. I'll code up exception handling. Do you guys want to see how exception handling works in the framework too? Yep, okay. Let's take a look at that, because that really comes into this piece here. So this is a demo that I really haven't prepped. This is completely off the fly, but that's okay. So what I'm going to do is inside my get cooks to make order method, inside my cook pizza, I'm going to say if, let's just go back to here. So you can see here's how I made it slow. Thread.sleep. My performance talk earlier, if you find a thread.sleep, that's probably the first place to look for performance issues. But in this case, this is for a demo. So what I'm going to do is say if order.pizza type equals, now I can't actually remember what my, okay, if it's vegetarian, I am going to throw a new exception saying out of olives. So if I run this now with my current code, which is not doing any exception handling, why did I do this for the third guy? I should have done it for the first one. Okay, it runs pretty slow. I'm doing it 3 times speed. Now I run this, and it threw an exception afterwards there. So that's chucked an exception, and because my code is not handling this, the whole code is just going to blow up. So we don't want that, because we don't want this to bubble out in unforeseen ways. We want to be able to access the exception at the correct time, and the correct time is when we're trying to access the result, because an exception is just another type of a result. We're not going to talk about monads or anything like that. I can see Ivan looking at me with a quizzical face. If you want to find out about that, see this man up the front. So let's go back to our method builder. We've got this guy here called run next method. Let's put a try and a catch on there. So if we've got an exception, let me see, did I do that right? Run next method goes down the bottom. Nope, I've put that in the wrong spot. Let me put that into the right spot. Okay, the method is going to iterate when we call move next. So numerator.move next. I'm going to put a try catch around this. Result. Okay. If result, keep running the rest. So that, okay, bool result equals true. Actually, let's not call that result. Has next. Okay, so if it has a next, now so the exception when it gets called will bubble up to here. So what I'm going to do is on this method here, this is something I haven't shown, because our async method builder itself, if we're going to chain this, needs to return a task. Because we need to be able to wait on this method. I'd shown you an async void. this here is going to now be an async type. So this guy here has got a task. Task equals a new task. Down the bottom, once we're finished, task dot set completed to be true. And at the top of this guy here, I can pull out the task. So what we've now done is wrap our collection of tasks that we're iterating over in another task, which means that we can wait on our method builder to run back. So just to show that, and the reason I've done that is that it's us that have got the exception if it bubbled out. So I can go on my task, task.exception equals X. I'm just going to create that property on my task. Cool. So let's just go back to Joe just to show that working. So Joe here, I've created my method. Where did my method builder go? I've got async await. I've put async stuff back in here, didn't I? Because I finished the demo. Let's go back to our version of the code. Dot run. Yep, there we go. Okay, so remember this guy here is now going to come task, method task equals async method builder dot our task. So we're pulling out our task. I can run that. That's going to return back a task. And just for now, I'm going to not really know how to do a continuation. Oh, actually, we know how to do a continuation. It's piss easy. Forgot about that. Method task dot on completed. Okay, so we can now have a method for on completed. And just to be a cheapskate, I'm going to pretend that setting an exception counts as completed. This is really bad. Task dot set completed. Okay, this in the real world would be set exception. Okay, but either way it means that the task is finished and we can signal to the person who's listening that that guy's finished. So back inside here, inside Joe, I should be able to put an exception catch here. I've got a try catch around every time I do it, and this exception is now not bubbled up, but it's just being stored as a property on my task. So if I just run this, and as I said, I haven't tested any of this. This is completely off the cuff. And let's see when this guy here happens. My task comes back, and inside my method task, if we just look at that, method task, which doesn't exist because I am inside a lambda. That would have been a real pain. I'm going to pretend I've got a continuation there. Okay, there we go. There's my exception. And this has come in there. Hopefully, I've got an exception on there, which I don't. So that didn't work. Anyway, you get the idea. That's basically what happens. So whenever, what's that? Okay. Yep, so let's just leave it for now. Basically, as we iterate through that, we do a try catch, and we put the exception on. But what happens with our async void is the exception needs to be listened to, or else it's just going to die into the ether. Exception comes back every time we use async, or every time we use await, exception gets bubbled up onto the current stack. So it's just going to keep bubbling up through the different methods. Cool, I'm on the slides there. So the exception keeps bubbling up through the different methods. So if we don't use await, our exception is just going to die. In fact, it goes onto an event handler when the garbage collection runs, which is about a minute later or 30 seconds later. And so you get some really crazy response, like a minute later when somebody clicks the fourth screen, it said there was an exception that was from 4 screens ago. So just don't do it. That's just your rule of thumb. That was a very long-winded explanation for saying that why. Likewise, be careful with async void. So we showed my method before that now returns back a task because our method builder wraps the child thing inside a task. If we use async void anywhere, we've got no way of waiting for the contents of that method. So the rule of thumb is async void is only ever for event handlers at the top of your stack. Never use async void unless you really know what you're doing inside the guts of things, because you're going to kick off a method like serving the customer or giving the order to the chefs, and you're not waiting for that method to come back. You just carry on with the next thing, like trying to give the order to the customer and you don't have any pizza because you don't know what's going on. Async void is the equivalent of that piece before where we did not await, and we didn't wait for that thing to be finished. Now, questions as I go through, just feel free to chuck them out there. Here's an interesting one where I also need to give you a little bit of background. Inside async, we've got a piece called a task scheduler. Now, task schedulers are really important, and this is where people get a bit confused. What that means is if we think about our threads before, so let's think about Bob and let's think about the other guys. When the cook said that they had finished cooking, in a threading world, that notification is actually coming up on the cook's thread. Okay? The cooks are the ones, as we saw before, they just said, when I'm finished, call any continuations, with no respect to how they might be called. But Bob's actually on a different thread. So we've actually caused a multi-threading issue there, because we've tried to execute Bob's work on the cook's thread. And the whole point of async is that we can write really simple linear code, and Bob's work works on Bob's thread, and the cook's work works on the cook's thread. So how the async framework does this is that when I register a continuation with the task, so if we go back to our code, when I call this onCompleted, what our code does is it says, instead of just calling the action, it actually stores a pair. Or actually it stores a wrapper, but we're not going to get in this. Pair, and then let's call this maybe calling parameters. Except there's no type called pair inside. Now let's use a tuple. Okay, so we've got our action, but we've also got some parameters around when we call that action, how should we call it? So when setCompleted is called, well, setCompleted is getting called from Joe's thread. Joe calls setCompleted from his thread saying, here's the action I want you to do when you're finished. And so when we call this, we check. So if, and here we can use, I'm just going to use some pseudocode because I'm not going to get into it. So if current thread dot needs to be run on its own thread, then we're going to store that along with the action. So that when we store that continuation of what we're going to run next, we store some details about this, of what thread it was that it was run on, or actually what dispatcher was being used. Synchronization context is the actual object that gets used. So what synchronization context was being used, which in a UI world is equivalent to a dispatcher. So think on a UI thread, we're adding it to the message pump. So when the message comes back, it's not going to run on the cook's thread, it's going to be added back to Joe's message pump. And I could code that up, but I'm not going to. Any questions around that? So async does this by default, only if the current thread has a synchronization context on it. So if the current thread has one, and all UI threads do, and IIS worker threads do as well, or you can put it on yourself by just setting one, then it's going to, when it comes back, come back onto its own thread using a post mechanism. So that's a bit expensive. I'm just going to go back. If it doesn't have a continuation, it's going to run on the default one, which is the thread pool. So if it doesn't need to do it, it's just going to run wherever it can, potentially on the current thread, potentially on the thread pool. What configure await does is configure await says, you don't have to come back onto me, just run this next bit of work wherever you like. And you want to use this from all your library code, because you shouldn't care how you're being called. And really from anything that's sort of database or backend that doesn't need to go back onto that thread. So if you're on a UI world and you call an async method, and then you need to call a network call and a database call and some other thing, anything inside that method, if that doesn't need to update the UI, use configure await, because it's not going to jump back to the UI thread. And anything we can keep off the UI thread is a good thing, because posting new methods onto the UI thread is a bit expensive. That makes sense? Unfortunately, we lose some of our nice syntax. So that's just a real bummer. But basically, any library code should be doing this. If you find any .NET framework methods when you're reflecting through that don't do this, then they should be. Async void can still be unit tested. Now, I mentioned before that you couldn't wait for an async void. I was lying, but in the majority you can't. But in the unit testing world, you actually want to. So let's say we've got a UI program, and we've got some button clicks. I want to be able to trigger my button click from my unit test and wait till all the threads are finished before I assert the result. But I don't want to make my method an async task, because if I make it an async task, then the exceptions that bubble out of that are not observed, and then we've got the issue around exceptions. So I have to leave it as an async void, and that's what the signature requires anyway from WinRT. What I can do is you can bastardize it. The synchronization context that I mentioned before actually takes a method called completed. So if you go take a look at this, I've put this up on GitHub. Actually, I haven't. I will put this up on GitHub after this presentation. You can use your own synchronization context for unit testing that then waits for all of the open async void tasks to complete before carrying on. This is really essential if you're doing unit testing around these things, because otherwise your unit test you just can't do it because your methods won't return. That make sense? That code's really invaluable, I've found. Just before I open up for questions, a couple of things about what's new in 2013. 2013's actually got a nice debugger. When you debug, should we show this? Yeah, let's see it. 2013 inside the debugger, I'm just going to completely ignore this demo class because I've stuffed it up like anything. And I'm going to unload that project. Oh, who knows what state it's in. Let me remove that from my master project, just so it doesn't stuff us up. And I'm going to open up, it'll still stuff me up because I'm not calling it, but we'll get there. At least the compiler will pick it up. I'm going to pick up this async one, which is really the same piece that we saw before, but implemented using async. So serve customer async, and inside this method, I'm just going to put a breakpoint here. So let's run and see what the debugger shows us. Yes, we expected build errors, which is because I'm trying to play that. Hit F5. If I hit the play async, which didn't actually break inside my method. Oh, there it is. It did break. I can now, there's a new tab inside Visual Studio under Windows called Tasks. And all things being equal, that should show me all the tasks that are currently active. This is including async void and everything else. We've also got a much better stack trace that actually shows through what was happening. This wasn't in 2012. There's a whole bunch of diagnostics that are in the framework now that allows this if you're running .NET 4.5.1. And we can see all the tasks that are open. So that's awesome when you're trying to diagnose stuff. Sorry, did I say 2012? So it's in 2013. Sorry, this is 2013 I'm showing. I'm showing the full RTM that came out 2 days ago and has blown up all my devices, but that's okay. I'm not bitter. We're fine. So really, that's what I wanted to share with you. I want you to be able to enjoy the magic of what's underneath it. It's actually not that hard. It's really, really simple what they do. But they've wrapped it in a way that allows us to write that procedural logic and make it really right the whole time. So I want to open it up. Questions. If you guys got any async problems that you want to throw out there, we can have a group clinic. Ivan can come up on stage and answer them. Anything that you want to know about async before I'm out of here. Go for it.
Yeah, so when you had that method which was going wait this, wait that, do this,
Yep.
using the final await syntax.
Yes.
You're going to put try catches around in there. Say if you just put it on the first await, then is this next bit still going to be run? You need to
Okay.
flow yourself. Where do you put the try catch?
So the question, if I understand it, was when you've got multiple awaits in a method, where do you put the try catches, and how do try catches work? Yep. Well, the way the framework's done, exactly the same way you would if you weren't using await. It works exactly the same from a coding point of view. And what the framework does in the compiler is it puts, if you put a try catch that covers 3 asyncs, inside that yield, it actually puts a try catch inside each one of those continuations with the same catch and then goes back to the same point. So the same with a using. If you put a using statement, it's only going to dispose it at the end, but it transforms it into a whole. So the real magic is what that compiler is doing. I'm not trying to get into that, but how it expands that method. But yeah, basically what it does is inside each of those continuations, it puts the same try catch going to the same catch result. Okay, sorry, so if you do a try catch around one method, and then you've got another method after the catch, you're saying? So that will operate exactly the same way as if you didn't have a wait. So if you're catching and then resuming, and you're not throwing that out of the catch, then your methods after the catch will still run. So think of, just remove the await words, and it's exactly the same logic. Okay? So exactly the same logic as if there was no await and it was a normal blocking synchronous method. Okay? Anything else? Nothing? I'm going to wrap it up then. So there aren't any more related sessions because it's now drinks time at the end of TechEd, which is awesome. But if you get a chance, take a listen to Ivan's recording. I'm looking really forward to listening to it. I haven't heard it yet. The blog from Stephen Tubb and the guys at Microsoft is really fun. It goes into all sorts of methods like how do you cancel something that's impossible to cancel and all these other sorts of crazy posts. John Skeet did a whole series of posts a couple of years ago that really goes through and basically expands on what I've tried to do today. It's a really good introduction to things. I'm on Twitter. You can catch me up later. At any stage, find me on a drink. I'm going to enjoy a drink in a second. And I want to say thanks to Lucky for those drawings that were done, because I sure couldn't have done those drawings by themselves. And I think they were pretty good. What do you guys think? Yeah, sweet. Okay, fill out your evals and let's get out of here.